naked, I'm numb, I'm stupid, I'm staying. And if Cupid's got...
Okay, so first of all, what is a second order ODE? Let's start off with that, the basics. So a second order ODE, and again, remember the order depends on the highest derivative that occurs in your ordinary differential equation. So this means an equation that contains a second derivative of some sort, a second derivative of our function, of our unknown function. Okay, and then everything below as well. So an example of that would be y double prime is equal to a function of t, y, and y prime. This would be a second order ODE in its normal form, okay? And normally what we see, we're going to be dealing with second order linear differential equations. So DE, differential equations, okay? And this one is usually found in the form of y double prime plus some function of t times y prime plus another function of t times y is equal to some function of t. This is what's called a linear, well, it is second order because we have the second derivative here, right? So it's second order and it's linear because we see the y double prime, the y prime, and the y are all on terms of its own. Like, we don't have like y prime times y double prime in any single term, right? They're all separated by plus signs, or minus signs in this case. And then we do have like our y prime or our y, or even our y double prime could be multiplied times another function of t, but usually we divide that out. Anyways, so the thing is that the y double prime, the y prime, and the y all occur in separate terms, okay? So here's like term 1, term 2, term 3, and then this one is just like a general, like, not general, but kind of a random function of t we could have on the right side here, okay? And so something special is also that when we have we could have two cases actually. So when our g of t here, and our g of t is called the forcing term, okay? Forcing term. And we'll cover this later as to why it's called that with reference to harmonic motion, which will be we'll learn in a couple sections, okay? So when g of t, when our forcing term is equal to 0, then that means that our equation, this whole entire equation here, our second order linear equation, that means our equation is homogeneous. Homogeneous, okay? So that would basically mean that we have y double prime plus p times y prime plus q times y is equal to 0, where p and q are functions of t, okay? And now, so yeah, that's pretty much it. And one other important thing to note about whether an equation is linear or not, you know how I said the y double prime, the y prime, and the y, they're all separated into separate terms, right? They're separated by like plus signs or minus signs or things like that. Okay, and they're not multiplied times each other. Also, we can't have, like, for example, let's say y is, we see y appearing as cosine y. We can't have that. It can't be stuck inside of another function. It just has to exist on its own, like this one here. Okay? Okay, so for our second order equation, second order ODE, ordinary differential equation, y double prime plus p of t times y prime plus q of t times y is equal to g of t. And of course here, our y is a function of t, as is y prime is a function of t, and y double prime is a function of t. We don't want our equation to look too crowded with t's and everything. Okay? So anyways, the first thing that we're going to cover after our introduction of the second order equations is existence and uniqueness. So existence and uniqueness, there's actually not much to it. So existence and uniqueness theorems are, this is the fun part, so are basically the same. For second order ODEs. Second order ODEs. As for first order ODEs. Okay, first order ones, ODEs. Except, so there is an except because there is one addition. Except now, instead of as for like initial value problems, so we're going to say except for initial value problems, and we're trying to determine uniqueness and everything, then we have to have, we now need two, not one, but two initial conditions, okay? Initial conditions, and I'll tell you why. Conditions, one for our function y of t, and another for now y prime, okay? Y prime of t. So I'll show you what this looks like on the next slide. So now we would be given a second order ODE, okay? So this would be like our y double prime, sorry, plus p of t times y prime plus q of t times our y is equal to g of t of some sort. And so this is the ODE part, right? This is the ODE part, and then we also have our initial conditions now. So we have two of them. So the first would be y of t naught is equal to y naught, right? And then we also need one for our y prime. So this would be y prime of t naught. So it has to be the same t value here for our initial conditions is equal to y sub 1, we'll say. Okay. All right, so that would basically be it. That's the only difference which distinguishes the existence and uniqueness theorems for, basically the uniqueness theorems, but anyways, the existence and uniqueness theorems for second ODEs as opposed to for first order ODEs. Okay? So now we'll go over the structure of a general solution. So general solution meaning not a particular one, but a set of solutions. Two, and we'll make this really specific because we want to start off with the fundamentals, right? So the structure of a general solution, 2, and let's see, the easiest thing that we could have for a second order ODE is homogeneous, meaning that we don't have a forcing term, or our forcing term is equal to 0, a linear equation, right? We only want to deal with linear equations at this point. Okay, so what does this look like? Well, first of all, a homogeneous linear equation looks like this. Y double prime plus p of t times y prime plus q of t times y is equal to 0. 0 because it's homogeneous. And now we're going to do some supposing, okay? So what I'm going to say, I'll just start off with this. So suppose y sub 1, which is a function of t, and y sub 2, which is another function of t, are both solutions to this equation, okay? To this homogeneous equation. I'll abbreviate. And then we have then y of t, which is equal to c1 times y1 of t. So this function plus c2 times y2, or y sub 2 of t. So this thing here, this expression, this is also going to be a solution. Then this is also a solution to, we could say for the constants, and C1 and C2 are constants, so for constants C1, C sub 1, and C sub 2, okay? So this is just a thing. We're getting to the structure of a general solution. This thing here is not yet the general solution because we need to specify one requirement for it, okay? But just in general, we're saying that, okay, let's say y1 of t, whatever that may be, when we plug it into here, into this equation, it satisfies our ODE. This is our ODE, right? And y2, the same thing. If you plug that into here, we also get that the equation is satisfied. So they're both solutions on their own. And then we're saying, okay, in this box here, we have some other function, which is created by multiplying each of our original, I guess we could say, our original, like y sub 1 and y sub 2 functions by some constant, and then we just add them together, okay? And this actually has a particular name. This is called a linear combination. Linear combination. I like to write linear combo, but you could write combination as well. So linear combination is called a linear combination of the functions y sub 1 and y sub 2. And again, that's obtained by multiplying each So I'll just write multiply, I can't write a y here, multiply each by a constant, and then add them together, and add together, okay? So that's how you get a linear combination of two things. Alrighty? So this thing here is true, that this solution in the box, this is a solution to our original ODE whenever we have that y1, y sub 1, and y sub 2 are already solutions to this ODE, okay? And now let's explore a special case, okay? A special and very important case.